404. That's the number of active National Weather Service alerts posted across the continental United States right now, at this moment, on a single calendar day in May. Not 404 watches and warnings spread across a week of bad weather. Not a slow accumulation from a storm system grinding across the country over several days. 404 simultaneously on one map. Here's what that map looks like. Wyoming is buried under late-season snow. Boston is flirting with all-time May heat records, thermometers pushing into territory the city hasn't seen this early in its entire recorded history. In the Central Plains, the Storm Prediction Center has issued a moderate risk for tornadoes, which is the kind of language meteorologists use carefully, because it means a real outbreak is likely, not possible. Down on the southern high plains, the Texas Panhandle, the same map shows extreme tier fire weather, the kind that turns a single spark into a disaster that outruns the trucks sent to stop it. And threading through central Missouri, there's a moderate risk flash flood threat, the fifth operational extreme on the same picture. Snow, record heat, tornado outbreak, catastrophic fire weather, flash flooding. 5 different flavors of extreme spread across roughly 1,500 miles, all happening at once. The meteorologists watching this aren't panicking exactly. They saw it coming in the models days out. But there's a word that keeps appearing in the discussions between forecasters when they look at a map like this, and the word is not unusual. The word is textbook, because there's an explanation for how all 5 of these things happen simultaneously, and that explanation is one mechanism, one pattern, one wave locked in place over the country like a hand pressing down on the atmosphere. That's the part that should stop you. Not just that 5 extremes are happening, extreme weather events happen. It's that they're happening together, in this specific configuration, because of a single underlying cause. One atmospheric structure is running all 5 disasters at the same time. The question is what that structure is, why it got stuck, and what the climate science community has known and said out loud in published research for a decade about exactly this kind of day. That single underlying cause has a name. It's called a Rossby wave. And if you've never heard of it, that's worth fixing, because it is the most powerful thing in the atmosphere that most people walk through their entire lives without knowing exists. Start with the jet stream, because that's where Rossby waves live. The jet stream is a river of fast-moving air circling the planet at roughly 30,000 feet, driven by the temperature difference between the cold Arctic and the warm tropics. The sharper that difference, the tighter and faster the jet runs, a clean, nearly circular band around the northern hemisphere. When the difference weakens, the jet goes slack. It starts to meander. It bends north, then south, then north again in long, lazy curves. Those curves are Rossby waves. They're not exotic. They're always there, always undulating. A Rossby wave is just the atmosphere's way of redistributing heat, pulling warm air north here, pushing cold air south there, keeping the system in rough balance. Under normal conditions, they travel eastward, completing a lap around the hemisphere in a week or two, and any one location gets a few days of cold, then a few days of warm, then rain, then sun. The weather changes because the wave moves on. But sometimes the wave stops moving. The technical term is wave resonance, a condition where the wave's own propagation speed cancels out against the mean flow of the atmosphere, and the whole structure goes stationary. It locks in place. The ridge sits over the same location for days. The trough digs over the same location for days. And everything that those two features generate, heat under the ridge, cold under the trough, violent shear at the boundaries, just accumulates in place with nowhere to go. Here's what makes a locked wave different from ordinary bad weather. An ordinary storm moves through. It brings 2 bad days, then it's gone, and the recovery begins. A locked wave doesn't give you recovery. It gives you the same forcing, day after day layered on top of itself. The soil dries out completely. The snowpack that's been building for days sends cold air pooling deeper into the valleys. The moisture streaming up from the Gulf keeps hitting the same front, over the same counties, every afternoon. The fire weather conditions that were already critical get another day of low humidity and strong wind on top. The wave isn't just causing weather, it's compounding it, and the specific geography of a locked wave determines which disasters end up adjacent to each other. Right now, the trough, the southward dip, is parked over the Rockies. The ridge, the northward bulge, is pushed hard into the east. The boundary between them runs straight down through the plains. That geometry is not random. It is exactly what produces simultaneous cold in the mountains, heat on the coast, fire conditions on the high plains, and a tornado and flood collision zone right at the scene. The wave didn't cause 5 separate events. It caused one event, expressed 5 different ways across the map. Start with the trough itself, the southward dip of the wave, anchored over the Rockies. That's where the cold pool lives, and right now, that pool is deep enough to put snow on the ground in Wyoming in May. Not a dusting. The Bighorn Basin picked up over a foot in some locations. Passes in the Wind River Range closed. The kind of accumulation you'd expect in late November, happening in a month when ranchers are already moving cattle to summer range and the wildflowers are 3 weeks into bloom. The numbers matter here. Temperatures in the upper elevations ran 15 to 20 degrees below the seasonal average. That's not a cold snap, that's a sustained displacement of the air mass. The cold pool isn't moving through, it's sitting, because the wave that created it isn't moving either. But here's why May snow in Wyoming is a signal, not just a statistic. The Rockies in May are supposed to be transitioning, snowpack melting, runoff feeding the river systems downstream, soil warming. When a cold pool locks over the range this late in the season, it stalls that transition. The snowpack gets additions it wasn't supposed to get. And then when the wave eventually breaks and the warmth finally arrives, it arrives all at once. Rapid melt, rivers overwhelmed, downstream flooding risk in a system that wasn't built to absorb it. The cold isn't just cold, it's pressure stored up for a release. And the same trough that's piling snow on Wyoming is doing something else entirely on its eastern flank, feeding the temperature gradient that's about to make May feel like July on the other side of the country. The eastern flank of a Rossby wave trough doesn't just mirror the cold on the other side. It amplifies it in reverse. Where Wyoming got a cold pool, New England got a ridge. And when a ridge builds over the Northeast in May, it doesn't deliver summer-like warmth. It delivers summer. Boston is reading temperatures in the low 90s in May. The average high for this week is 63 degrees. That's not a nudge above normal. That's nearly 30 degrees above it, and the record for this calendar date is within reach or already broken depending on which station you're watching. Here's what built it. The same locked wave that dropped the trough over the Rockies forced compensating high pressure to pile up downstream. Ridges don't just warm the air, they compress it. As air sinks under high pressure, it warms at a rate of roughly 5 degrees Fahrenheit per 1,000 feet of descent. By the time that air reaches the surface along the coast, it has been mechanically heated from above, not just from the sun. The sky can be clear, the humidity can be low, and the thermometers still push into territory that belongs to late July. And the humidity matters here for a different reason. May in Boston is not August in Boston. The region hasn't heat adapted yet. People haven't pulled air conditioners out of storage. Urban cooling centers aren't on alert schedules. The infrastructure, the bodies, the buildings, the public health response is calibrated for spring. When the air disagrees with the calendar by 30 degrees, that gap between expectation and reality is where the danger lives. The ridge is also not moving. Because the wave is locked, the high pressure that built over New England is anchored there. A heat event that would normally last 2 days before the next frontal system sweeps through is instead sitting, baking, accumulating. Each day, the ground absorbs more heat. Each night, the temperatures don't drop far enough to release it. The baseline climbs. Boston is an extreme, but it's a quiet one. No sirens, no tornado warnings, no wall of fire. Just thermometers reading numbers the calendar says are impossible. And 600 miles to the west, under that same locked wave, the atmosphere is doing something far less quiet. 600 miles west of Boston, the atmosphere is doing something far less quiet. It is building. The Central Plains sit at a convergence zone that exists almost nowhere else on Earth. To the north, that same Arctic cold pool anchored over the Rockies is pushing southeast, dense and heavy, riding along the surface. To the south, the Gulf of Mexico is open and warm in May, evaporating moisture by the ton and funneling it north on a low-level jet that runs like a river of invisible fuel. And overhead, the jet stream, the one that should be meandering in a slow drift towards summer, is instead locked into a sharp, fast, southward dipping blade directly over the plains. 3 air masses, 1 collision point, a jet stream blade to provide the rotation. The Storm Prediction Center does not issue a moderate risk lightly. It is the 4th level on a 5-level scale. It means organized, significant, long-track tornadoes are not just possible, they are expected. The maps this morning showed a corridor running from southern Nebraska down through Kansas and into Oklahoma, where supercell thunderstorms were forecast to initiate by mid-afternoon, rapidly intensify, and produce multiple significant tornadoes. The shear values, The difference in wind speed and direction between the surface and 5 kilometers up were extreme. The moisture was deep. The cap, the layer of warm air that normally prevents storms from firing too early, was just thick enough to hold everything down through the morning heat of the day and let the instability build to dangerous levels before it broke. That is the setup. This is what it looked like from the ground. A storm chaser working northeast of Dodge City, Kansas, called in a report shortly after 4 in the afternoon. His voice on the spotter network was level, measured, the practiced calm of someone who has seen this before, but the words were specific. Wall cloud lowering rapidly, hard inflow from the southeast. Rotation confirmed on the meso, debris signature on radar. He called the tornado as it touched down, gave the bearing, gave the direction of motion. Then, 30 seconds later, it is widening. That storm was one of several discrete supercells operating simultaneously across the corridor, each one drawing from the same collision of Arctic air and Gulf moisture, each one organized by the same overhead jet. The locked wave that dropped snow on Wyoming and baked Boston also built this. Same mechanism, different face. This one rotating at the ground, moving northeast at 45 miles per hour, and already flagged on the warning map as a significant tornado emergency. The planes are armed today, and 200 miles to the southwest, under the same wave, something else entirely is happening. Something with no clouds at all. 200 miles southwest of that tornado corridor, the sky is completely clear. No rotation, no supercells, no rain. Just open blue and a wind that has been accelerating since dawn. This is the Texas Panhandle, and right now it is under an extreme tier fire weather watch, the highest operational category the National Weather Service issues before a fire weather emergency. Here is what the same locked Rossby wave does on its backside. The trough that dropped cold air down over Wyoming also built a powerful ridge of high pressure across the southern high plains. As air descends from that ridge, it compresses, warms, and dries. Meteorologists call it adiabatic heating, the same physics that gives you a hairdryer. Every 1,000 feet that air drops, it gains roughly 5 degrees Fahrenheit and sheds humidity. By the time it reaches the surface at 4,000 feet of elevation, it has been wrung almost completely dry. The relative humidity readings across the Panhandle today are running between 7 and 12%. The critical fire weather threshold is 25. These numbers are less than half of that. When humidity drops below 15%, fuels, dead, grass, shrub, the residue of last year's drought, stop behaving like biological material and start behaving like tinder. A spark doesn't smolder, it propagates. And then there is the wind. The pressure gradient between the locked trough to the north and the surface high to the south is steep enough that sustained winds across the region are running 30 to 40 miles per hour, with gusts already clocked above 60. That is not a wind advisory. That is a structural component of extreme fire behavior, the kind that outpaces a running person, that jumps roads, that causes a fire that was manageable at noon to have burned 40,000 acres by 4 in the afternoon. The Texas Panhandle has been through this before. The fires of February 2024 torched more than 1 million acres in a single week, the largest in state history at the time. Today's conditions are statistically comparable. Same wave geometry, same descent, same moisture deficit, same wind structure. There are no clouds here to telegraph the danger. No radar signature, no wall cloud, nothing visually dramatic. Just a landscape quietly reaching ignition threshold in every direction, waiting for one vehicle sparking a guardrail, one downed power line, one anything. The map is red. The ground doesn't know it yet. 400 miles northeast of here, in central Missouri, the atmosphere is doing the opposite, stacking moisture until the rivers don't have a choice. Stacking moisture is the right phrase. Central Missouri is sitting under a warm, moist tongue. Meteorologists actually call it that. A channel of Gulf air being pumped northward by the same pressure architecture that's baking Boston and starving the Texas Panhandle. The air is wet, not humid in July wet in a way that's structurally unstable, where the atmosphere is essentially a compressed spring looking for any excuse to release. Here's what that release looks like. Storms firing to the southwest train. They don't move off quickly. They reload, cell after cell, rolling over the same river valleys, the same creek drainages, the same towns. The first inch of rain saturates the ground. The second inch has nowhere to go. By the third, the creeks are out of their banks before the radar even shows the worst of it. A moderate risk for flash flooding from the Weather Prediction Center is not a common issuance. It means forecasters have high confidence that rainfall rates will exceed what the land can absorb, that water will move fast enough to be genuinely lethal, and that the threat is concentrated enough to be specific rather than diffuse. It's the second highest category they issue. Most counties never see one in a given year. The specific danger here isn't the dramatic kind. It's a road that was dry at 7 p.m. and has 6 inches of moving water across it by 9. It's a driver who's crossed that same road 100 times, making one miscalculation about depth and current. Flash flood deaths in the United States, more than any other weather phenomenon in an average year, are almost entirely that story. A moment of familiar terrain that stopped being familiar. The instability numbers over Missouri right now are among the highest in the country. The atmosphere overhead is carrying enough convective energy to sustain rainfall rates that can dump 2 to 3 inches in under an hour in a localized area. And the rivers in this part of the state were already running above their seasonal average before a single storm fired today. The ground was already soaked. The spring was already compressed. What's coming is the release. That release, the one building over Missouri right now, was not a surprise to the people who study the atmosphere for a living. Not this specific storm, not this specific day. But this configuration, this locked wave, this simultaneous spread of extremes from the Rockies to the Atlantic seaboard, they wrote the papers, they built the models, they gave the pattern a name. The science goes back roughly a decade to a cluster of research that started asking an uncomfortable question. Why were extreme weather events increasingly arriving in coordinated clusters rather than as isolated incidents? The old assumption had been that weather extremes were essentially random, bad luck distributed unevenly across a large country. What the data kept showing instead was something more structured. When extremes clustered, they clustered in ways that tracked the shape of large planetary waves. The same wave that caused a heat event on the East Coast was, predictably, causing a cold event somewhere upstream. The same trough that dried out the southern plains was funneling moisture into the Midwest. These weren't coincidences. They were the geometry of the atmosphere, made legible. 2 mechanisms became central to this research. The first was Arctic amplification. The Arctic is warming roughly 4 times faster than the global average, and that shrinking temperature contrast between the poles and the tropics is what gives the jet stream its energy and its tendency to stay roughly on track. Weaken that contrast, and the jet stream slows down. It starts to meander in broader, deeper curves. And critically, those curves become more likely to get stuck. The second mechanism was wave resonance. Atmospheric scientists identified that certain wave configurations can become self-reinforcing. The wave's own structure creates conditions that prevent it from propagating eastward the way it normally would. It becomes locked in place, amplifying in intensity while it sits. The technical term is quasi-resonant amplification. The practical meaning is that whatever weather the locked wave is producing, it just keeps producing it. Days turn into weeks. Records don't just get broken. They get broken repeatedly, in the same place, by the same pattern. What the models predicted a decade ago was that this would happen more often as the climate continued to warm. What the data is now showing is that it is happening more often, and earlier in the seasonal calendar than the models anticipated. The window for these locked configurations was supposed to expand gradually. Instead, the expansion is outpacing the projections. Events that the models flagged as late-century risks are arriving in the middle of the century, in the middle of May, across a map that currently has 404 alerts on it. The scientists who wrote those papers are not surprised by what they're seeing today. That is, in some ways, the most unsettling part of this story. This was the predicted future. It just got here faster than predicted. So why is it still here? That's the question the forecasters keep getting asked, and it's the right one. If this pattern is causing so much damage, why doesn't the atmosphere just move on? The short answer is that the wave locked itself. The longer answer requires understanding what locking actually means in fluid dynamics. Because it isn't a failure of the atmosphere to function exactly as it can under conditions that tip it into a stable configuration it can't easily escape. A Rossby wave moves when there's a gradient strong enough to push it. Under normal conditions, the temperature contrast between the Arctic and the mid-latitudes creates a tight, fast jet stream, a river of wind that sweeps disturbances downstream, west to east, clearing the board roughly every 5 to 7 days. That clearing is what most people experience as weather that changes. A storm comes, a storm goes. A heat wave breaks, the pattern resets. But when the Arctic warms faster than the mid-latitudes, which is what's been happening at roughly 4 times the global average rate, that temperature gradient weakens. The jet stream slows, and a slow jet stream meanders. The waves it carries get bigger and more pronounced. And at a certain amplitude, a wave can interact with the underlying terrain, mountain ranges, continental land masses, temperature boundaries, in a way that creates a resonance. The wave stops translating downstream and starts oscillating in place. That's wave locking. The atmosphere isn't broken, it's resonating. And resonance, by definition, is self-reinforcing. What breaks the lock? Eventually, energy bleeds out of the wave, or a strong enough impulse, another disturbance. A burst of upper-level energy from the tropics, a shift in the sea surface temperature is feeding it, disrupts the resonance. The pattern collapses, the jet stream tightens again and sweeps the whole configuration downstream in a matter of days. But eventually can be a long time. And while the wave sits, the people under it don't get to wait. The firefighters on the Texas Panhandle have now worked their 4th consecutive day in red flag conditions. The flash flood watches in Missouri are being extended, not lifted. The heat building along the eastern seaboard isn't peaking, it's still rising. Each additional day a locked pattern holds is not a repetition of the first day. It's an accumulation. Soils get drier, fire perimeters grow, river levels climb. Infrastructure that was designed for 3 days of a heat event strains at day 6. The wave will move, the pattern will break. But the question the climate data is now forcing into the open is how often this will happen and for how long each time. Because if the conditions that lock the wave are becoming the background state, then the calendar between events is what's actually shrinking. So let's put the numbers on the table, because this is where the abstraction ends. On a single calendar day in May, the National Weather Service had 404 active alerts in force across the continental United States. Not cumulative, not over a week. 404 simultaneously on one map, under one locked wave. Snow accumulation advisories in Wyoming. Record-threatening heat watches along the eastern seaboard. A moderate-risk tornado outbreak, a designation that affects less than 5% of all severe weather days in any given year, over the Central Plains. Extreme fire weather, the agency's highest operational tier, across the Texas Panhandle. And a moderate-risk flash flood threat over central Missouri. 5 separate extreme tier designations, from 5 separate meteorological hazard categories, active at once. When statisticians talk about the probability of compound events, they don't just multiply the individual odds together, because these events aren't independent. They share a cause. The locked wave produced all of them. But even accounting for that dependence, the probability of hitting the extreme tier across 5 distinct hazard categories simultaneously is a number that has no historical precedent in the modern observational record. Researchers who study this say the same thing differently, depending on their discipline. But they arrive at the same place. We don't have a baseline for this, because this hasn't happened like this before. And that's the thing about records. A record temperature in Boston in May is a data point. A record fire spread rate in the Texas Panhandle is a data point. 5 data points from 5 categories on the same day stops being a collection of anomalies. It starts being a signal about the state of the system itself. The records falling here aren't falling because the atmosphere had one bad day. They're falling because a pattern that used to be rare enough to be treated as exceptional is now occurring with enough frequency that the infrastructure designed around the old statistics is visibly failing to keep up. 404 alerts isn't a number that fits inside the old frame. It's the old frame breaking. What it means going forward is this. The question used to be whether a day like this could happen. The question now is how far apart those days will be, and the gap is closing faster than the model said it would. The gap is closing. That's the only honest place to start the ending. The wave will break. It always does. Eventually, a downstream trough deepens enough, or an upstream blocking pattern shifts, and the jet stream lurches back into something closer to its old course. The snow melts in Wyoming. The heat breaks over Boston. The fire crews on the Texas Panhandle get a wind shift and a few points of humidity back. The floodwaters in Missouri recede. And for a day or two, the maps look almost normal. But the conditions that built this pattern, the Arctic that has warmed 4 times faster than the global average, the reduced temperature gradient that slows the wave and lets it anchor, the moisture-loaded Gulf that turns any instability into something violent. Those don't reset. They're the new floor. Every wave that forms now forms on top of them. Every extreme that develops has more fuel than the same extreme would have had 20 years ago. The pattern breaks, and then it reforms, and the next one starts from a higher baseline. The models already show it. There's a second wave loading in the Pacific right now. The ensemble forecasts have it making landfall on the west coast in roughly 8 days and carving east. The exact placement is still uncertain at this range. That's normal. But the amplitude is not uncertain. It's large. Whether it locks the way this one locked depends on the atmospheric state it finds when it arrives, and that state is determined by what doesn't fully recover in the interim. That's the part the old framing misses. It treats each event as a separate incident. A bad week, an anomalous spring, a once-in-a-generation map. But if the recovery time between events is shrinking, and the events themselves are more intense, then what you're actually watching is a system that no longer fully resets between shocks. It keeps some of what happened. It carries it forward. 404 alerts. 5 simultaneous operational extremes. A Rossby wave locked over a continent while the Arctic bleeds heat it was supposed to keep. This is not the worst day the models describe. It is closer to the median of what the next 30 years look like, if the trajectory holds. The wave will move. The next one is already forming.